So we come to the exercise for the third lecture. Just the first question was, what is the fill factor of the solar cell, shown at page 132. This was the page with the various IV curve with different illumination levels, and it asks the fill factor for 1000 watt per square meters and 200 watt per square meters. Also was asked the conversion efficiency at those irradiance levels, considering area or cell size of the cell 10 by 10 centimeters. Then it's also asked which ohmic load resistors have to be connected to the solar cells in order to operate them at the maximum power point, MPP. Then the second part of the exercise was that you have a solar factory that's producing 1 gigawatt under standard test conditions per year. And if you would switch from the standard test conditions to the nominal operating conditions, how would then be the output? What would be the last part is what would be the relative power output of a multi-crystalline PV module if we integrate that module into a roof and temperature increases, sure. And we take a look at this table and page number 137 and then determine the power loss and the yield loss. So let's start with the first part here. This have been the IV characteristics, and now we have to find out at 1000 and 200 watt per square meter. So we take a look here. The red points, the red stars are the operation points for the maximum power point. So we go there, and we see at 1000 watt per square meter, the voltage in the maximum power point is around 0.36 or 37 volts, and accordingly the current in the maximum power point is 2.75 amps. We take a look at the open circuit voltage on a short circuit current. The short circuit current is 3.0 amperes, and the open circuit voltage is 0.455 volts. Then also for the second illumination level or second irradiance, this is at 200 watt per square meter. So the voltage in the maximum power point is 0.338 volts, and the according current is 0.56 amperes. Also, the short circuit current is 0.6 amperes, and the open circuit voltage for the illumination level of 200 watt per square meter is 0.414 volts. So if we put these numbers we got here from the graph, if we put it into the formula for the form factor, which is voltage in maximum power point times current in the maximum power point divided by open circuit voltage times short circuit current. That is then for 1000 watt per square meter, we saw the voltage in maximum power point was 0.370 volts. The current in the maximum power point was 2.57 amps, and the open circuit and the short circuit current are 0.455 volts and short circuit current 3 amps. So altogether we have a fill factor of 0.745. If we go to 200 watt per square meter here, we have short circuit 0.6 amps, current in maximum power point 0.56 amps, and a voltage in maximum power point 0.338 volts, and open circuit voltage 0.414 volts. We put it into the formula here, and then we have a form factor of 0.762. That means it's increasing at lower irradiance level. Not very much, but we can see it here. More important is the conversion efficiency here. This is output power, which is electrical power. This is the voltage in the maximum power point times the current in the maximum power point. The input power is actually the irradiance times the effective area. So if you put this value in, so we have here the same as here, 0.370 times 275 volts times amps, which is watts. Then irradiance level, global irradiance is 1000 watt per square meter, and the area 10 centimeters square by 10 centimeters square is 100 centimeters square, and that is 0.01 square meters. And that is then 0.102, so 10% of conversion efficiency about. For 200 watt per square meter, we put the adequate numbers in, same as above here. The irradiance level is 5 times lower, area stays the same, and then we have a conversion efficiency of 9.46% only. So we see, due to this weak light effect, the conversion efficiency is going down. That's a pity, because in times when you have low irradiance level, you additionally have additional losses, and you don't get proportionally the power output, you get a bit less. This depends very much on the purity of the materials, because this is determined by this resistor RP, which is bypassing some of the current and accordingly of the power. Let's go to the next part. Which ohmic load resistors we have to connect to the solar cell to operate them, and the MPBP. So we want to extract the maximum power possible. So the formula, just ohmic law, voltage divided by current is the ohmic value, and that is for 1000 watt per square meter. We saw the adequate number, so voltage in maximum power point is 0.37 volts, and the current in the maximum power point is 2.75 amps. So then we have a resistor which we have to put there to be adapted of 0.135 ohms. If we go to 200 watt per square meter, voltage is sinking a little bit, but main effect is that we have about a current which is about 5 times less than initial current, and accordingly we have a resistor, an optimal resistor of 0.604 ohms. We come to the second part. Is asked about the solar module factory, which produces 1 gigawatt. This is P. This index P indicates peak. That means that is related to standard test conditions. It's not really physical. It's just a costume in an industry that they use this P to indicate that this power has been measured at standard test conditions. Divided by year, also 1 gigawatt production of solar modules per year, and we want to see how the output of that factory would switch if you would use more realistic conditions, the nominal operating conditions, and we take for the temperature coefficient, we take multicrystalline silicon cells as a reference. So just the reminder, the operation condition at standard test conditions is 25 degrees Celsius of the cell, not of outer temperature, and the irradiance is 1000 watt per square meter. And this is this is from the table here. We take a look at the temperature coefficients here. What we have here, so we see for the power output is minus 0.44% per Kelvin. So for 10 degrees more temperature, we would have 4.4% less power output. Here the NOCT, which you take here, this is 25 degrees Celsius. That means if you compare it to standard test conditions at 25 degrees, we have additional temperature of 20 degrees. Here we see it, so temperature, and also what has to be considered at the nominal operating conditions. It's not taking this 1000 watt per square meter. There we only have a more realistic value, which is 800 watt per square meter. So we lose both by the temperature and by the more realistic irradiance level. So as I mentioned already, the temperature difference is 20 degrees. And the power output according to nominal operating temperature. So we have a correction factor of the two different irradiance level and one correction factor due to the more realistic increased temperature by 20 Kelvin. So if we put in the numbers, so the initial value was 1 gigawatt peak here, and these two irradiance values was 800 versus 1000 watt per square meter. And here we have one plus the temperature coefficient, while the temperature coefficient negative, we have minus 0.004 if we substitute the percent per Kelvin, and then we have the temperature difference here of 20 Kelvin. So at the end, our proud 1 gigawatt power plant actually has 729.6 megawatt only. And that's the reason why these nominal operating conditions are not often used. They are more realistic, but factory owners don't like it because the actual values seem to be significantly lower than the values under standard test conditions. Last part we have, if we have a multicrystalline PV module, and if we would operate it instead of a rack on a free field on a roof, it increases temperature as we saw, and we take a look at the table here. So we see here if we would have a rack mount here, then we would have a nominal operating cell temperature. For example, we saw it was 45 degrees, while the convection is better at a rack mount. Then we can take off 3 degrees, so actually it would be 42 degrees only, so we gain some power. In contrast to that, if we would integrate it here on a roof mount, direct mount, then we would have 18 degrees more. That means we would have higher operating temperature, less voltage, and less power output. So we see that the total temperature difference is 18 plus 3 Kelvin, so 21 Kelvin. And altogether, if we compare the two power values, we arrive at 90.76%. What we saw, we lose about 10% in power and energy yield if we mount our module differently. Thank you very much. Just an outlook to the next lecture. So we will talk more about the manufacturing of solar module, its specific characteristic, performance. And then we would switch to PV systems, where we talk about wiring, inverters, grid-connected system configurations, the so-called mounting, and so-called BOS, that means balance of systems costs, off-grid versus on-grid systems, and the costs. Just an announcement, while we probably can't do an excursion, we would switch the lecture number 12 from the excursion to a more theoretical background of photovoltaics. Thank you very much.